Welcome back to AI.Code.Cast, where we take those deep dives into fascinating coding challenges. And today, we're tackling a classic one that often pops up in those technical interviews and, well, real-world applications, too. It's all about finding root-to-leaf paths in a binary tree, but not just any paths that add up to a specific target sum.
Yeah, it's a problem that really tests your grasp of tree traversal and, coming up with efficient solutions.
Okay, so before we get lost in the weeds here, maybe you can remind us what exactly is a binary tree and how does this whole pathfinding problem actually, work?
Absolutely. So picture a tree, but kind of upside down. At the top, we have the root node.
The root, okay.
And each of these nodes, they can have at most two children, a left child and a right child.
Like branches?
Exactly, branching out. And each node also holds a value, which could be, say, a number. Now, our goal, it's to find all the paths from that root all the way down to the leaves, those nodes at the very bottom with no children, where the sum of the values along each path, equals that given target sum.
Okay, I'm with you so far. So it's kind of like a treasure hunt in a tree. Like you're trying to find all the paths that lead to the treasure, but only if the numbers along the path add up to the right amount.
Exactly, you nailed it. And the challenge lies in finding all those possible paths, not just stumbling upon one.
Right, right. So if we just like blindly tried every single path, wouldn't that get super inefficient? Especially if the tree was like massive.
Oh, absolutely. That's what we call the brute force approach. And, it might work for those teeny tiny trees, but as the tree grows computationally, it just becomes way too expensive.
Yeah, no, that makes sense. So brute force is out. What's a smarter way to tackle this? Any hints you can give?
Well, think about navigating a maze. You wouldn't just wander around randomly, right?
No, you'd probably pick a direction and keep going till you hit a wall or, you find the exit. And if you hit that dead end, you backtrack and try a different path.
You got it. That's the core idea behind depth first search, or DFS as we call it. It's a super powerful algorithm for exploring these tree structures.
Ah, DFS. I've heard of that. It's all about going deep, exploring one branch all the way before you even think about backtracking, right?
Bingo. Now, how can we apply that same thinking to our binary tree problem here?
So as we go down each branch, we got to keep track of the running sum of those values, right?
Yeah.
And if we hit a leaf and the sum matches our target, boom, we found a valid path.
Precisely. And if the sum, goes over the target or we reach a leaf and we're not there yet, well, we backtrack and try a different branch.
Backtracking, that's key here to make sure we're checking all the possibilities, but not getting stuck in a loop.
Absolutely. And, there are a couple of ways we can actually implement this depth-first search. We could do it recursively, or we could go the iterative route using a stack.
Wait, recursion? Isn't that a little risky? I always get nervous about those infinite loops.
Don't worry, we'll set up those base cases to avoid any disasters. Recursion can be really powerful when you're dealing with trees like this.
Okay, I'm willing to give it a shot. But before we jump into, like, actual code, can we walk through how this recursive approach would work, like, conceptually?
Sure thing. Imagine a function, let's call it checkPath. This function, it takes the current node, the running sum, and a list to store the current path.
Okay, so at the very beginning, that current node would be the root of the tree, the sum would be 0, and the path list would be empty.
Exactly. Now, inside this checkPath function, we add the value of the current node to our running sum, and we tack that node onto our path list.
So we're keeping track of where we are, where we've been as we go. Got it. What's next?
All right, so now we check our base cases. If we've reached a leaf node and our running sum matches our target, bingo, valid path. We add that to our list of results.
The eureka moment. But what if we're at a leaf and the sum's off, or we go over the target before we even get to a leaf? What happens then?
In those cases, we know we've hit a dead end. We don't do anything. And the cool thing about recursion, the function automatically backtracks. It returns to where it was called, essentially going back to that last decision point.
So the recursion handles the backtracking for us. Pretty neat. But what about exploring those other branches?
If the current node isn't a leaf, we just call checkPath again, but this time for both the left and right children. We pass along the updated running sum and the path list, of course, and that's where the recursive magic happens.
Ah, so we're basically repeating the process for each branch. And recursion is handling the exploration and the backtracking for us. I'm starting to see why this is so elegant.
You got it. It's a concise and powerful way to do DFS. But like you mentioned before, recursion can be a bit memory hungry, especially for those really deep trees.
Right, because each recursive call adds a frame to that call stack. and that could lead to those Stack Overflow errors. So how do we avoid that potential pitfall? You mentioned something about using a stack.
That's right. We can implement DFS iteratively using a stack data structure. It's kind of like manually managing what recursion does automatically.
Interesting. So we're creating our own stack to keep track of what to explore, instead of relying on the program's call stack. But how does that actually work in practice? Break it down for me.
Welcome back to AI.Code.Cast. We're in the midst of, well, dissecting this challenge of finding those root-to-leaf paths in a binary tree, the ones that sum to a specific target.
And right before the break, we were starting to tease out this idea of using a stack to handle our depths for search. It sounds like a way to get that systematic exploration we need, but without those potential memory issues that recursion can have.
Exactly. It's a trade-off, You might end up writing a bit more code, but you gain a lot more control over the whole process.
Control is always good, especially when you're dealing with like potentially gigantic trees. So walk me through how we'd actually use a stack for this. I'm all ears.
All right, so picture this, our stack. It's like a to-do list for the nodes we need to explore.
A to-do list. Okay, I like that.
We start by pushing that root node onto the stack, along with its initial running sum, which, starts at 0, and an empty path list.
Okay, so we're prepping the first item on our to-do list, getting it ready for exploration. Then what?
Then we enter a loop, keeps running, as long as our stack isn't empty. Inside that loop, we pop the top element right off the stack.
Popping it off, okay.
And that gives us the current node, its running sum, and the path leading to it. It's like picking up where we left off on that specific branch.
Yeah, it really does mirror that recursive process, but with like much more explicit steps. I like that.
Right. And just like before, we check, is this node we just popped off a leaf? And does the running sum equal our target? If both of those are true, bam, valid path.
Another celebration moment.
Oh.
But what if it's not a leaf? Or the sum's not right? What happens then?
Well, just like with recursion, we know we need to explore further, but instead of that recursive call, we push the children of this node onto our stack.
Adding to the to-do list.
Exactly. Both the left and right children, updating the running sum and the path list for each, of course.
Okay, so we're branching out, adding new tasks to our exploration list. But how does the stack handle backtracking, if we hit a dead end?
That's the beauty of the stack. It's that last in, first out behavior. When we've fully explored a branch, we naturally pop it off. The loop keeps going, processing the next item, which is essentially that last point where we had a choice to make.
So we're automatically retracing our steps without needing that explicit function call. The stack itself is guiding the backtracking. Very clever.
Exactly. And by managing the stack ourselves, we avoid those potential stack overflow errors that might crop up with, really deep recursion. So it's a trade-off, right? A bit more code complexity, but we get more control and robustness.
Okay, that comparison makes a lot of sense. But now I'm thinking about, how we're storing all these paths as we go. Could that get pretty expensive memory-wise?
That's a great observation. You're absolutely right. Storing all those paths can really eat up space, especially when you have large trees with tons of valid paths.
So is there a way to be even more clever about how we manage this path information, like some sneaky trick to save space?
And this is where things get really interesting. We can actually slash that space complexity by shifting our whole perspective. Have you ever heard of inverted tree traversal?
Inverted tree traversal. Honestly, that sounds kind of like something from a sci-fi movie. Does it involve, like, turning the tree upside down?
Not literally,
Yeah.
but it does involve a bit of a mental flip. The core idea is we focus on finding those valid leaf nodes first, and then we reconstruct the paths, but in reverse.
Wait, so we find the ends of the paths first, and then trace our way back up to the root. How does that even work? Welcome back to AI.Code.Cast, where we're, wrapping up our deep dive into finding those root-to-leaf paths in a binary tree. The ones that add up to that specific target sum.
And we've covered a lot of ground. Brute force searching, the elegance of depth-first search, both recursive and iterative, and even, that pretty mind-bending inverted tree traversal.
But right before the break, we threw a bit of a curveball at our listeners. What if, instead of finding all paths that sum to the target, we wanted to find the shortest one?
It's a twist, right?
Yeah.
It takes us from just finding paths to, actually optimizing for the best one, kind of like navigating a city. You might have a bunch of ways to get where you're going,
Right.
but some are going to be shorter, faster, depending on traffic construction, one-way streets.
So in our binary tree world, how do we figure out which path is the shortest? Do we have to, like, find all the valid paths first and then compare how long they are?
Well, you could do that, but it wouldn't be the most efficient way, right? Remember how basic depth-first search just explores every single path without really considering any other factors?
Yeah, it's like a wanderer who just takes any path they see without caring how long it is.
Exactly. To find the shortest path, we need algorithms that are a bit more, well, strategic. They need to factor in the cost of each path as they go.
Cost. So we're not just adding up those values along the path anymore. We're assigning some kind of weight to each step we take.
You got it. In our shortest path problem, that cost could be the number of nodes in the path, or maybe the sum of edge weights if we're talking about a weighted tree, or even something way more complex depending on the application.
So we need algorithms that can keep track of all these costs and then, like, make smart choices about which paths to explore first. It's like having a GPS that considers not just distance, but also traffic and tolls.
Perfect analogy. And there are some classic algorithms out there designed for exactly this, algorithms like Dijkstra's algorithm or search.
Okay, those names are ringing a bell, like, way back from my algorithms class. But I'm a little rusty. Can we get a quick refresher on how they actually work?
All right, so picture these algorithms as like super smart pathfinders. They have this priority queue of nodes to explore, and the priority is based on the cost to reach each node.
Okay.
So the nodes with the lowest cost, those that are closest to our starting point, those get explored first.
So it's not just a random exploration like with basic DFS. It's way more organized.
Exactly. And as they explore, they update the costs of those neighboring nodes, taking into account the cost of the path leading to them. Like, you know how your GPS updates your ETA as you hit traffic.
So these algorithms are constantly adjusting, reevaluating what the best path forward is based on what they're learning.
Precisely. And this keeps going until they hit that destination node. And because they're always prioritizing the lowest cost paths, that first path they find, guaranteed to be the shortest.
Wow, so it's like they're cutting through all the noise and finding the most efficient route without wasting any time on those unnecessary paths. Way more efficient than just trying everything and comparing lengths.
Absolutely. Those are essential tools for solving all kinds of shortest path problems, not just in binary trees, but graphs, networks, real-world scenarios.
This has been a wild ride through the world of binary trees and pathfinding. We went from basic depth-first search all the way to these advanced shortest path algorithms. It's amazing how a problem that seems so simple can lead to, like, such a deep exploration of algorithmic thinking.
And that's what makes coding so fascinating, right? It's problem solving, creativity, constantly searching for those elegant and efficient solutions.
Well said. And to our listeners, keep exploring, keep experimenting, keep those coding brains fired up. Until next time, this is AI.Code.Cast, signing off from the Deep Dive.